Great. Good morning, everyone, and good evening, Thomas. Thanks, everyone, for joining us today. Today, it's my pleasure to introduce Thomas Wolf. Thomas is co-founder and chief science officer of Huggingface. His team is on a mission to catalyze and democratize NLP research. Prior to Huggingface, Thomas gained his PhD in physics and later a law degree. He worked as a physics researcher and the European patent attorney. I also really wanted to thank Thomas for accepting our talk despite his busy schedule and despite our time difference with Europe. Please join me in welcoming Thomas and enjoying his talk.
Hey, thanks a lot for having me. And so in this talk, I'll start to briefly introduce Huggingface, and then I'll talk about the science topic that interests us at Huggingface. Okay, so it's quite an unusual talk. I do that very briefly. No, not very often in the year. I mean, and so basically, Huggingface started as just a group of people interested in conversational AI, interested in, that was the beginning of GAN and all this kind of generative AI, this kind of use of machine learning model to have generation capabilities instead of only predicting, only like classifying and only doing this kind of thing. And so we were interested to see if we could embed that in a game that would be a bit like a chatbot. That would be a bit like the Tamagotchi, if you're old enough, you know, the thing that was in the 90s. So we made this game with a very like funny character you could interact with. And while we were building this thing, we kind of started to open source a few tools that we had. And some of these tools were using the beginning of transfer learning. That was GPT-1, I think, actually, and even before, actually, DeepMoji, which was the first case where transfer learning was really, really successful in NLP, I think. And this tool actually caught a lot of interest from the community, so much that after about a year, we were just fully working on these tools. And so we decided to kind of change the goal of the company and to move to this idea of using the tools we build to catalyze and to democratize all the research level work in NLP. So we are interested in both NLU, natural language understanding, but also natural language generation. We think both are important. I actually talk a little bit about that in the talks, so we can discuss this. And we do this catalyzation in two ways. The first one is knowledge sharing. So that's why I'm here today to talk. And that's also why we do a lot of also organization at the MNLP. We're organizing a workshop called Sustain LP. We also organized NeuralGen. Well, there was also a conference that was canceled due to COVID, but we were supposed to do the second European NLP Summit this year. And so we do a lot of things like that, knowledge sharing. And also we do what we are mostly known for, obviously, is code and model sharing. So we try to do what I call open sourcing the right way, which is to find the right balance between pure research code, which is like a snapshot of a research project, which is nice, but if you want to adapt it to another project or use it actually in another application, you usually have to rewrite the script from scratch because it's just made for one specific project. And you have the other extreme, which is like production code, which is usually one line, very efficient to write because the end goal is very clear, but then it's usually not flexible enough for research work where you want to play with the model, when you want to modify it, when you're here to create kind of new stuff. And so we try to find the right flexibility point just in the middle. And we also like to break all these barriers that we see that are between frameworks, PyTorch, TensorFlow. We don't think it's really important to choose one or the other. And we think you should be able to choose the one you like. And also between researcher and practitioner, we think the frontier is much more blurry than people think. Like the tasks that we study are obviously deeply inspired by research application, by real use case. So we also try to make the framework so that can be used basically by both. And so very briefly, because I won't really talk about that, but more about science, but we have today's three main libraries. The first one that you probably know is Transformers, which is a library of state-of-the-art models with a model hub, where people can upload pre-trained models. So the idea here is that training this big model is very expensive, and so you should be able to reuse this compute that people have burned to train this model. You shouldn't have, if you want a baseline, that was the beginning idea at the very beginning, you shouldn't have to train this baseline again just to get the baseline for your paper. You should be able to build on top of this paper very easily by getting access to not only the code, but also the artifacts that were created during the research work. So this is one of our library. The second one is maybe a more practical one, is called Tokenizer. It's a library to do very fast tokenization. And it's now incorporated in transformers. Tokenization being this step where you transform strings in the numbers you need to like input in your net. And the last library we've open sourced just before the summer, and I've been actually working quite intensively last week because we did an open project where people could contribute, and we had about 300 people joining the project. So it was really crazy, and it's ended just today. And so this is a dataset library. We also think datasets are a bit spread across the internet. It's sometimes hard to find them. Sometimes it's difficult to pre-process them. And basically you spend your time rewriting pre-processing code that many people have already written. So this dataset library, which is called Datasets, is a library which lets you very easily access about 500 datasets now, and we will soon have more. So we cover a really wide field of NLP dataset. And it also provides you some metrics, because we come from natural language generation background, and we know there are some really cool metrics, but they're also very complex to use sometimes, like BLERT, or like these recent metrics that kind of use a pre-trained neural net. And also kind of old metrics. If you want to use Rouge, you never really know which one you should use between the 4 possible Rouge metrics that are out there. And so we decided to kind of make this also easily accessible and kind of standardized. So this is this new library we've been working a lot on. And it also lets you do other stuff that are maybe less important or not, but the idea is that you should be able also to train on very large data set that kind of exceed the size of your RAM memory, for instance. So we made this possible by just using like more recent backend. We use something called Apache Arrow, which lets you use your hard drive as a RAM drive, basically. And this lets you train on basically any size of data set without any limitations. So it's quite exciting. So these are our 3 main libraries, right? So I spend a lot of time doing this because I think the tools are very important to actually be able to do research. But we also have a research team that do a lot of things. And today I'm going to talk about this mainly. So let me switch presentation to switch to the other one. This way. So it's a fairly long presentation. It's normally about 1 hour. So what I will do is that I think I will go a little bit quickly over it, and then we'll talk about the part that you like more, okay? Can you still see it full screen? I guess you do. Okay, Huggingface. So in this talk, I want to talk about the future of what we do. So Huggingface has been since the beginning really interested in transfer learning. We think this is a new technique, which, well, new technique's not really new, but this is a technique which is here to stay. While our main library might be called transformers, I think transformers are maybe something that will change, but I deeply think transfer learning is something that is here to stay. And so today I want to talk about what are the limits to question and where to go. So it's very subjective work. It's basically a work about over all the papers I like. So I did this talk. I studied this at the Nordic Language Processing Winter School, actually early this year, and then people liked it a lot. So I decided to make it a smaller version. Instead of 3 hours, just make it one hour. Okay, and so I cover basically what's happening with model size, what's happening with computational efficiency, which is maybe the tip of the iceberg that everybody has heard about, even more now because GPT-3 has been around now. Then I talk about out-of-domain generalization, model evaluation, which are two things that are deep problems right now. Talk a little bit about fine-tuning these models, sample efficiency, and then end up with common sense and inductive bias. Okay, let's start about exponentially bigger models. What's happening there? Yeah, everything is a little bit on slide because I actually usually have my own face here, but I won't do these complex tricks to include me in the slides right now. So you just have a little bit of white space on each slide. So you've probably, well, I don't know if you've seen, but the Victor made this graph like last year when he released this Dilbert, which showed just how many parameters people have been having in their models. And what you see basically is that right now, if you want to reach the state of the art on like typical benchmark, well, pretty much any benchmark, unfortunately now, is that you have to use a model which is at 1 billion parameter or over. So this was done early this year. So the biggest model was T5 with 11 billion, but now we also have GPT-3 with 100 billion. And we also have Google G Shard with 600 billion. And Google G Shard, they actually even trained a trillion model. Well, they tried to, but it wasn't really successful. So this is a big problem, right? There is, I think, at least three main problems here. The first one that you see here is that if you look at the Glue leaderboard, you just see basically Google, Baidu, Microsoft, Facebook, but you see just no academia here, okay? So that's a very big problem. I think, what is the place of academia in today's NLP? I think, what should they do? Are they like here just to fine tune this model, just to understand them and to do biology? As they're just there to critique them and say, okay, that's not the right direction? But there's a big question. Yeah, what should we do? And how to go forward from here, I think. The other problem is called, is related to training this model and how much compute we burn. And I think Emma Struble was maybe the first one to kind of state that in this ACL paper last year, kind of computing how much the carbon dioxide we were releasing when training this model. Well, the thing is that transformer maybe not the worst if you do like neural architecture search that fortunately not many people do in NLP. You really crazy amount of compute, but there is still a question here, because today that's definitely a very big debate. And the last one, I think, is the most important, I think, in my opinion, is where we're going with this. Is it a scientific program just to make models bigger? I think François Chollet has often likes kind of know well how to put things in words, and then saying how training bigger models is a bit the same than trying to build taller towers to reach the moons, right? And so even though GPT-3 is now the best paper at NeurIPS, we still wonder, okay, where do we go from there? Is it like, do we expect, that's what I talk about in the next slide, and I should actually go faster because I'm only on slide 5, but do we expect to see basically a phase transition where if we big enough, we reach like some models that qualitatively behave differently? Or is it just like this small increase? Okay, we've doubled the size, but now we're 5% better. And now we double the size again, we are getting 5% better. So this is a big question. I'm kind of in the field who think that we're going to reach a phase transition, but this is the research program of companies like OpenAI, obviously. Now you can go the other way. That's what we have been doing a lot at Huggingface, is trying to find a way to make this model smaller. So one thing is that since this nice paper of Yann Lequin, I like the title, Optimal Brain Damage. It sounds like a rock band. We know that these neural nets have too much parameters. Well, we don't know if they have too much, but we know that we can at least remove parameters and still keep pretty much the same performances. So this is also related to the low certificate hypothesis, decided that in the models, in the sufficiently big models, you have like subnetworks that already have good performances on your task even before you train them, okay? Yeah, so that was last week, 2 weeks ago now at TMNLP. We did this workshop called Sustain LP, where we try to actually set up new incentive. We think that we mostly lack incentive in the research community to research smaller model. Well, now it's better, I think, in the end of 2020, but in the beginning of this year, there was definitely a lack of incentive to be interested in this smaller model because they just don't get you to the state of the art on your typical benchmark, right? So we did a competition to try to stimulate this, where people had to find the most efficient model on superglue. And actually the best model here had like a 200 improvement in speed and also in reduction in energy consumption. So that you can actually do some pretty impressive improvements. So how do you do this reduction of size? Today you have three main techniques. We have been kind of playing with them all at Huggingface. Distillation is the first thing we tried last year with a model called DistillBird. And distillation is this idea that once you have a teacher model that you've trained, which is pretty big, you can, well, typically, which can be very big, you can train a student model, which will be smaller, but will keep most of the performances. And the idea here is that you will use the full probability distribution outputted by the teacher model. So you train the student model to try to reproduce. Here you have just a typical cross entropy where you try to push the student model to reproduce basically the probability distribution outputted by the teacher model. And what you can see is that if you take a BERT model here, so it's trained with masked language modeling. So you mask a token and it's trained to try to predict the missing token. And you can see that the probability distribution, all the options basically make sense. So this is what we call kind of generalization. There's a generalization that the models learns that the missing token, so this is a sentence extract from Casablanca, I think, the movie. I think this is the beginning of a beautiful, and the models say, okay, maybe it's day, life, future, story, world. They're all kind of okay. And basically your student will learn to reproduce this. So there are many ways you can see distillation, but one way I kind of like is to see as kind of soft labels. Basically, you're using this other possibility outputted by the teacher as kind of soft labels through the cross entropy. So you can control this with a soft max. And this worked quite well. This basically the idea is that you here have the best of both worlds. So you will have a large model that will learn to generalize quite well. And you will have then that you use during your training. And then for inference, when you want to deploy the model in production, you will train a smaller model that reproduce most, that take advantage of all the inductive bias learned by the large model. So there's been a lot of other work. You can do that a lot more complex. I think DistillBird is the most complex distillation setup. And actually this paper is so complex that it's kind of hard to know where the improvement comes from, because they use at the same time data augmentation and two-step of distillation and also some mimicking between the hidden states. So there's a lot of like crazy tricks here. I kind of guess like half of them are probably not so useful, but this is the state of the art right now, tiny birds. And they reach very good performances at the end with all this. I think that the main problem in this paper, I think, is that data augmentation kind of blur the situation and don't really know what is the advantage come from data augmentation and distillation. So, but this is the state of the art in terms of small size, at least early this year. I've not checked actually what's happened last week at TMNLP. Now the other thing you can do is that instead of training a smaller model, you take your teacher and you just prune it. So you have many ways to prune. The first thing that people kind of saw was that you could remove heads. That was the nice paper by Elena Wojta from Edinburgh, and also Paul Michel at UW, at CMU, sorry, showing that basically you can remove a lot of heads in these transformers and you keep the performances quite well, quite good. This is on translation, subtitles, and this is on glue. So it works on a variety of you have on variety of tests. You have various ways to identify the important heads. This is the nice head importance score by Paul. And then you can also do just basic weight pruning. You just take each weights and you remove them. Now, if you remove each weights, you have a little bit of problem, because then you end up with a sparse model. And if you know a little bit sparse model, they are not very compatible with GPUs, basically. So you have a small model, but it's very slow at the same time. So alternative are to use layer pruning. This is also a nice paper by Angela last year, where you remove the layers. And this is nice because you keep your dense matrices. And here the idea is that you have to prepare a little bit the models to do that. So during the pre-training, you kind of stochastically remove the layers so the model is ready to have some layer removed at the end. And so now there is, yeah, as I told you, there is this trade-off between how you do your sparsity and how much your model is not or is still compatible or not compatible with GPU. So if you do layer or head pruning, you keep dense matrices, so it's okay, but you also constrain the pruning, okay? And if you do like just random sparsity or like just a normal sparsity, you are very flexible in how you can remove the weight. So you usually get good performances, but then you're slower. And you can find alternative, which are called block sparsity. So we have actually, if you follow what we've done this summer, we have our open source library called PyTorch block sparse, which is all about that. So block sparsity, the idea is that you will remove by blocks. You can see this here on the right here. So you will remove blocks, and the idea is that you keep the size of the blocks here. These are the blocks, just the right size for your CUDA kernel. So for your GPU, it's okay. It's pretty much like dense matrices. You usually have a 2x slowdown. But then if you reach a good enough sparsity, then you could have actually speed improvements at the same time as you have like a smaller model. So block sparsity is one of the most promising method, and we actually have a paper coming out quite soon on how this works quite well actually. And the other option is to use something other than a GPU. And GraphCore is one company making something called IPU, which are specifically designed for sparse matrix multiplication. But this is not super easy to access right now. Now they are on Microsoft Azure, but for a long time they were just like in private beta. Okay, and now quantization, you kind of know what it is, I guess. You move from float to integer, and it also works well. Won't spend too much time because it's not super exciting. Okay, now this was about the size of the model. Now let's talk a bit about the data. While the models, they are bigger, they also train on bigger and bigger data sets. And this causes a lot of other problems. So the first one is how we compare these models. So I think it started last year when there was this new model called XNet that kind of were better than BERT, apparently. But the main thing was that actually this model was trained on about 20 times the same amount of data than BERT. And when you try to put them side by side, well, so XNet also had this new architecture where they were trying to do something which was at the same time bidirectional and autoregressive. So they have like a random permutation, and they kind of, well, that's complex to explain, but they did like at the same time something that was somehow bidirectional in that the model used the left and right context and also was autoregressive. And so they kind of put that forward, say, okay, this is the best thing. This is the important thing in the results. But when you kind of put these models side to side with the same training data, XNet and BERT, it was definitely not clear that the architecture was the reason, and maybe it was just that they used 20 times more data. And I think the discussion was settled when Roberta went out just after, and Roberta used yet again more data and was just better than XNet. So that was the bittersweet lesson, right, of deep learning in NLP, that just more data is better than a smarter architecture. And Roberta has exactly the same architecture than BERT. That was the idea, was just to take BERT and to try to scale it in terms of training data. And then came all the GPT, and the GPT had this super simple architecture, which is really dead simple. And they just work fine because they use a lot of data. So that's one thing. And then that's during pre-training, right? And then during fine-tuning, we have also the same problem where we do this kind of data augmentation. So I think this is more evident on the Winograd schema challenge. So I think this, for a long time, the Winograd schema challenge, the WSC, was, I think, one of the most interesting NLP tasks, at least the most challenging, because it was quite small, but still very, very difficult to solve. So the idea is that you have these coinference tasks. So you have a sentence, the trophy would not fit in the brown suitcase because it was too big. And the model is asked what was too big, the trophy or the suitcase, okay? And so normally you should just use kind of common sense to say that something which is the trophy typically go into suitcase and not the other way around, okay? and it's very small. It has, I think, 600 examples. So it's definitely, it was outside of deep learning thing. And the way it was kind of solved, because now it's considered, this data set is kind of considered solved, was that people generated very large data augmentation things. So just basically scrapping Wikipedia and just replacing the sentence where you have 2 times the same noun by a coreference pronoun at the second position. So they build this very, very big data set called MaskWiki with just these heuristics. And this was in this 2019 paper. And this basically solved this task. But that kind of pose the question, okay, what have we learned here? And I think to me, we just have learned nothing at all about the underlying question of common sense, right? Which was the idea of the Winograd schema challenge. There was like a task was about common sense, and just doing this heuristics augmented way to solve the task is, I think, deeply the bad way to try to solve this task, I think, in terms of advancing science. So yeah, okay, now more, maybe yeah, so and then I have a little bit, okay, let's maybe talk a little bit time. So I have a little bit more details on the 2 things here. So I spent a little bit on pre-training and then a little bit on fine-tuning, okay? Pre-training, I just want to show this paper. Now it's quite known, but just before the summer, it was not super known. So this is one of the nice, actually, paper by OpenAI, which is called Scaling Laws for Neural Language Models. And they show that basically, as you scale these models, the size of the models in terms of computer parameters or in terms of dataset size, you have some very clean way of predicting how how the performances will improve. And this is what actually was kind of intuitive. A lot of people have emit this hypothesis that you have this exponential relation where you need to double the size of the model to get a linear improvement. This linear thing that sometimes people call that plateauing of performances. But they kind of show that empirically in a very clean way, I think, in this paper, just that this is the way these models behave in terms of how you vary the size of the models or the data set. And they also kind of explore a lot of things that people were doing quite intuitively, the ratio between the size of the various layers, the ratio between the number of heads and the different parameters. And they show that all this kind of probably how we were expecting, but now this is kind of show all this is really not really important as long as you're in the sweet spot that we were actually already in. So this sweet spot that was kind of originally found, at least in the attention is all you had paper, that was pretty good. But this is a nice paper if you want to really see this clearly investigated, I think. And they show that actually training bigger models on than we usually do on some types of data set was more data efficient, which was kind of interesting as well. And then the question here is this OpenAI kind of question and I want to show you maybe one data point that I find interesting, also because it's not from OpenAI. So as I told you in the beginning, there is this question: do we expect if we make models bigger, or on the other hand, if we train on more data, do we expect to see something fundamentally changing? Like, so I come from a physics background. We can call that phase transition. Do we expect that somehow, at some place, we move to models that behave qualitatively differently? And I think this paper, like just last year by the group at Tel Aviv, the AI2 team at Tel Aviv, shows something interesting. They compared BERT and Roberta. And as I told you just before, BERT and Roberta, they have exactly the same architecture. It's exactly the same model, same number of parameters. The only difference is how big the pre-training corpus was. For BERT, it was trained on just just a small kind corpus of 13 gigabytes, and Roberta is trained on a corpus that's about 10 times bigger, 100 gigabytes, which is about this. And when you ask them, when you investigate on a kind of a common sense task, which is a zero-shot task, and here the task is like this: you have a sentence, a 25-year-old person is than a 38-year-old person, and the model has to predict this if the missing word is younger or older. So it's kind of common sense, at least how you handle ages. And you see that BERT is in blue, and BERT is quite bad. But raw data, just with more data, you kind of see this phase transition if you want to see it. You see that this model is just right in pretty much all the cases. And you can do something a bit more complex when you reverse the birth year. So here, instead of asking about age, we ask about birth year. And this go the other way around, right? If your birth year is higher, if you're born later, then you're younger. And it's okay, like Roberta is not so bad. It's a bit more complex, you can see, but it's not so bad. And if you ask about the relative size of many objects, like is an airplane bigger than a laptop? As you can see, it's really pretty good. So yeah, this is kind of one data point that could say, okay, maybe there is something happening just because we use more data. And I think now it's a bit more, even more impressive, I think, with the biggest GPT-3, which was not, which I did not include here, but that's this idea. Now, this is the idea about getting to more data. But now I think the idea here is that, well, the main underlying question is, do we actually think this model generalize better, or do we just think we just cover more in the training set so that they actually don't really need to generalize better, but they just seen what we offer? And I think it's pretty clear that we go kind of to this in this second thing, which is it's not really about more generalization, but it's more about they just seen like pretty much all situation, right? So and we see that in fine-tuning as well. So I talk about the number of data, the data amount in fine-tuning. Okay, when we try like to augment the, well, we augment the fine-tuning data set with more thing. And here the main problem in the end is how we compare this model. So I think this paper was very nice by Yogatama. It was learning and evaluating general linguistic intelligence. And the question here, this example is maybe the best, like how we evaluate this model. So we take one model, let's say model A, we train it, we fine tune it, for instance, and it's reached like 90% accuracy, but it reached this accuracy with just 110 training sample. So very quickly, but then it's kind of plateau because yeah, there is nothing, you cannot reach higher. But model B, take 1 million example to get to 90, but then it plateau at 92. And so the way we compare our models right now with like the benchmark we use like glue or like, yeah, all these benchmark would lead us to say, okay, model B is better. Model B has won the academia competition. This is where we should go from now. But definitely model A somehow is actually the model we should start from if we want to make improvements. And so what they push for in here is to basically stop also evaluating these models, putting them all on the same foot and saying, okay, we compare just this GPT-3 with this BERT, with this Roberta. Well, they are all use different amount of data, okay? And instead what they propose is to kind of explore how the model behave with the number of data as the number of data is increased. So it can be during pre-training, but in this paper, they mostly focused on during fine-tuning. And they use something called online code length. This is also a nice paper if you like information theory view of learning. And the idea is that with each additional example, you actually try to see how the model improves. And so you take each additional example in the training or the fine-tuning sample, and you see how the model improves. And if it improves a lot with each additional example, actually it means the model is very data efficient because it can learn a lot with just one example. And if it's very small, then it means your model is not data efficient. And so they show that actually, they show with this new metrics that you can compare model in another way. So this new informational metrics, which is code length metric, it's related to actually if you want to transfer your model with information theory. But yeah, okay, let's just talk about that if you want to know more about that in here. But this gives you, here you can see that we vary the number of examples on the bottom. And this gives you a different view of how the model learns. You can see that some models will like learn very quickly here. Some models kind of start high, but they kind of plateau. And this is probably a better way to compare them. And it's, yeah, so it was also, so I just showed you this paper here about quantitative job. They actually did the same investigation about the training efficiency. And you can see also here that actually Roberta, which was, you remember, better in this kind of common sense evaluation, Roberta is also a lot more data efficient. So there is some kind of interesting relation between how these models, when they are trained with more data during the pre-training, when you fine tune them, they also learn more quickly with each additional sample. So this, I have not seen a lot more follow-up on this, but this was also kind of interesting. But I show that, yeah, basically these fine-tuning curves here, investigating what happens with the number of training examples is the way we should go from now to understand how these models actually behave. And this is basically all related to this play with between in-domain and out-domain. So you have in-domain is kind of, if you can see, it's kind of all that is, if you want in your pre-training, you can see that, depends where you start, but you can see that all is what is in pre-training data. And then you, as you fine tune and as you go in real world settings, you have these out of domain examples that come. And you would like the model to behave also well on this out of domain model. And I think one thing we've realized is that while these very big models, they are kind of quite good on in-domain data. And one possibility, like what is done with GPT-3 and things like that, is just to try to make every data in domain. If you take a model which is not trained on the whole internet like GPT-3, but which is trained on some part of it, like BERT, they're still not very good on out-of-domain generalization. When you ask them something that was not in the way they were trained or fine-tuned, they're kind of lost. They have worse behavior in generalization than we thought they had. I think one of the best paper on this was the Hans dataset by Tom McCoy, group of Tal Linsen. And what they did here is they investigated what happened on MNLI. So MNLI is this natural language inference where you have two sentences and you're supposed to say if one sentence entails the other, one sentence contradicts the other, or they're just neutral. And so you have this very big data set with two sentences. But the thing is that, and you can train models with very good accuracy on this thing. You can train right now. So this is part of the GLUE benchmark, and you can reach like 90% accuracy on this, well, it's F1 accuracy on this data set. And one thing which is interesting here, this is the core of this paper, Bert of the Feather, is that when you train models which are very, very good, they have good accuracy on this data set. And when you test them on out of domain, they can generalize all in different ways. Some of these models, so the main difference between all these models here, they train like about 20 models, I think. The main difference is just the random seed that they use for the fine tuning. And all these models, they can reach the same performances, but when you train them on out of domain, so out of domain here means that you will try to, yeah, just for instance, here you have more lexical overlap between the sentence than in the original data set. And they're all generalized in different ways. Some of them will be pretty bad with almost zero accuracy. Some of them will be medium good with 0.5. And this is something that you can't really predict. And it's very surprising. And we have the same when you train a model on a specific data set of question answering, for instance, on Squad, and you evaluate it on another data set of question answering, like Trivia or Quack SRL. You would think that if the model has really managed to learn the underlying task, it would kind of extend to like related data set of the same task. But what we observe in practice is that it just don't really work. This model, they fail, and they fail in a way that you don't really expect. It's a bit like here. Depending on the random seed, they would work more or less good. And it's really hard to know why they work or not work. There are a few examples here. So here it's at the same time, in all cases, it's a model that was trained to, all these models were trained to basically the same accuracy on the training set, on the training dev set. And when you test them on this out of domain data set, which is Hans data set, you see that they generalize in really different way from each other. Yeah, this is a bit complex. I will just switch this. And one core problem here also is how do you measure how far you are from your training distribution? And this is actually very hard because we don't have a very clear metric that say, okay, we're in the same field under training data set. We're out of the training data set distribution. So you have a lot of possible metric. You have a lot of way you can actually, you have a lot of feature representation on which you can base this metric. And it's definitely not clear and not investigated that much which matrix is the most relevant one and or which way we should measure the dataset distribution shift between the testing and the training dataset here. Okay, so now that was something about in domain, out of domain. And now I want to talk a little bit about the rise of NLG, which is something I like a lot. And the idea here is that there is a fundamental limit to we've talked a lot about data efficiency and how much your model can learn from one example and or a few examples, and how it's important that your models can learn with just a few examples, which is basically the promise of transfer learning. And here there is a fundamental limitation in the way we used to do transfer learning in the beginning, which is that we used to add a classifier or like a task specific layer on top of the model. And this task specific layer, which is, for instance, just designed to cast the output of the model along 2 or 3 tasks, for instance, if we have a 2 or 3 task classification task. And this layer that we had will always be randomly initialized, basically. Yeah? So we have to train it. So this means that we cannot really just do zero-shot learning. We cannot say, okay, with one example, or like just one-shot learning, with one example, you should learn a task, because there is this layer with maybe a thousand parameters, basically, that we have to train. And so one solution that has been emerging this year, and actually started last year, and the premise, I think, was the Brian McCain paper on of Cephas on the natural language decathlon. One idea was that maybe we can just use text-to-text model. So text-to-text model, they will take some text as input and generate some text as output, okay? And you can cast, that's the magic of language, right? Language, the natural language is a meta language, so we can formulate tasks using language, basically. And so we can cast all the NLP tasks that we have, we can cast them as text-to-text task. So instead of being a text classification task where you predict one of 2 class, the model will generate positive or negative, for instance, at the output. And now the nice thing about this is that we can pre-train the model in text-to-text fashion. And when we move to the downstream task, we just use the same model. Now we don't have any new parameter to adapt to our task. We're just trying to fine-tune the model. But if, like, for instance, the downstream task is close to the pre-training task, we can reach the few short learning setup. And so this was shown in GPT-2, which was one of the paper where they started doing that. They started to cast all this. Well, the original one was the DKNLP multitask learning paper, but more recently was the GPT-2 paper, where they cast a lot of tasks as prompt, post-prompt generation. For instance, translation, you will have a sentence in English, and then you will have French, and then the model will try to complete. And if these prompts kind of look like the training set, the model will try to complete with a French sentence. And this worked quite well. In particular, in tasks like Lambda is actually a closed prediction task. So it works really well. On some tasks, on some other tasks, it works a little bit less well. And this has been the biggest trend recently in this large scale model, which was this text-to-text thing. So Facebook BART was an encoder decoder model that was trained in this text-to-text setup. And then they did a multilingual version of BART, so BART is a Facebook model. They did a multilingual version. And more recently, there was Google T5, which was also text-to-text. Actually, T5 is text-to-text transformers with transfer learning, where they also did this pre-training with encoder decoder, and then using all the downstream tasks as text-to-text. Yeah, okay. So I think this is a very interesting thing. And more recently, if I want to talk just about last week at EMNLP, two weeks ago, there was a nice paper, I think, by Matthew Peters and team at LNAI, which was proposing to actually even get out of defining an NLP task as a set of example in NLP, but actually defining the task as just instruction. So instead of saying, okay, now the task is entailment, and we'll give you 10,000 examples of entailed and contradiction sentence. Now the idea here is that you just say, okay, the task is entailment, and that's your training. That's the only input that you have for your model. And then if your model, then the challenging thing is how can we actually work with this kind of thing where we can totally leave the idea of stochastic training and just using an example to learn one task. But I think that's definitely where we should go, basically using language as a meta learning, as a meta language. Okay, now I had this thing, but the situation is a bit solved now. But early, there was some problem with lack of robustness in fine-tuning this model. We can talk a little bit more, but I think now it's a bit more robust than it used to be just before the summer. But there is still these two things. So let me highlight these two limits. So there's these two main limits to how the model generalize. I think they are related to two kind of phenomena that we often conflate. The first one I think is brittleness. So brittleness, the main paper where it was shown was I think the early one was Robin Jian, Percy Liang. This was the adversarial example for squad. And they show basically that if you add some sentence at the end of a paragraph of squad, while the model was trained on the normal, like this kind of pretty much always the same size paragraph, and also with never any distractor like this, the model is very easily lost. So if this means that if you basically leave a little bit of training distribution, depending how you formulate this, but if you leave a little bit of training distribution, you can very easily get this model to be lost. So this is one problem that we call brittleness. And spuriousness is a little bit different. Spuriousness, we also talk a lot about that, is the idea that if you have an easy heuristics that lets you solve your data set, then this very large model will very quickly catch it. So in MNLI, which we've been talking a little bit about, there is a few easy heuristics that people have actually found later on. And one is called lexical overlap. And that's the idea that if you have a lot of lexical overlap, so you remember MNLI, the idea is that you have two sentences and you have to predict if one entail the other or if one contradict the other. And basically, if you look in the data set where you have a lot of words in common in these two sentences, it's usually entailment, the correct class. But here you see that it's very easy to construct example where this is wrong. For instance, here, the first sentence is the doctor was paid by the actor. The second sentence is the doctor paid the actor. So the meaning is different. In the first one, it's the actor who paid, and the second one is the doctor. So they're actually total contradiction. But you have a lot of words in common. And just because you have these easy heuristics of lexical overlap that the model will catch because it doesn't have to like dive into the meaning, but can just stay on the surface form of the thing, just the model will be always wrong in this thing. So this is what we call spuriousness. I think it's Anna Roger which kind of coined these two distinction. And yeah, this is very annoying spuriousness for us because these models, these large models, they are very fast learners, and they will very quickly learn these easy heuristics, and they will stick to them. But the end result by these two problems is the same, is that the model will just fail out of domain, and they will fail in a way that we don't really predict. And if you want to say, okay, how can we solve that? There is many ways, but I think it's some place where linguistics can help, and linguistics should help basically. Basically, first, it's probably the best way to kind of detect this thing, because we have this way to kind of understand language as it was designed, or as at the meaning level and not just the surface level like we do. And so we have a way to design tests to design this like lexical thing. Like, and it's also a nice place to try to build tests for the model. So you can design evaluation here, and you can also design artificial text test for, like, I think this paper is very nice by Duke. It's a fairly long paper in Journal of Machine Learning Research last year. And they kind of designed an artificial language based on compositionality behavior. Here, they also define what is compositionality, sorry, it may be the best way I've seen recently. And by building this kind of artificial language that reproduce really the linguistics concept that we would like the model to pick up. And here they also made something called naturalization, where they make the artificial language reproduce the same statistics than a real language, a very large corpus, the WMT, 19 translation data set. And so they have like an artificial language that can really look like a language, but where they can control what's happening and investigate where the model fails in out of domain generalization. And here it's easy when you build the language yourself with kind of linguistic thing here. It's easy to control out of domain. You can just remove like one type of structure, of compositional structure, or you can just use one word or like combination of words just in a test domain, and then you have very easy way to probe out of domain generalization. And what they show is that the model basically are really not very good on this. Transformers are better than LSTM. And it's also a nice paper where they compare really different architecture together for the first time. I think not a lot of papers are really comparing what's happening in Transformer and LSTM, and also ConvNet in this paper. But we are really far from having like a successful like model that really work well out of domain. Now, another way we can try to investigate this or like to fix this, if you want, is to dive in the architecture and to try to put some linguistics in the architecture. So there was a nice paper by Emma Strebel, but also this graph ConvNet here, where we try to kind of put the pass tree that we know inside the architecture. So that's kind of the other way. Instead of trying to learn that from the data, you just try to put it in architecture. And more recently, there was a funny paper by Nafis, where they actually try to give some linguistic hints also to the model, but in the training data, adding like the predicate argument structure in the training data. So just trying to use linguistics to tell the model, okay, there is more than just surface form. There is something here, there is a structure that you can learn, and this could help you get the right inductive bias to kind of extend out of your training data. So one way is this kind of linguistic approach, one way to try to solve the out-of-domain generalization. And another way is to say, okay, the main problem is actually not that the model does not understand like linguistic and the structure of the sentence. The main problem is that the model just don't have any common sense. And I think these are kind of just orthogonal directions of reflection. And here the idea is that there is a lot of kind of common sense that also the model just cannot learn from text. So this is, I think, also something very important. It's called the human reporting bias. And this was a paper by Ben van Duurm in 2013. And it's the idea that we usually don't write things that are very obvious. So I usually take the example of the white sheep. We don't really say that sheep are white, the animals, they are white. But we talk a lot about black sheep. And so when you ask even a very large model, we tried it actually 2 weeks ago, we tried it with GPT-3. When you ask it what color is a sheep, it doesn't really know. It say half of the time white, half of the time black. But we know this is definitely, there are a few black sheep, but they are very rare. And that's why we use this expression to say, okay, this is like a rare element here. And they just don't know that, and they cannot learn that very easily just because it's not written, because it's boring. And so we just don't write this down. We only write the thing that we find interesting, which are the things that are just not common sense usually. So the main way to try to overcome this in my opinion, well, one way is obviously to try, if you get just as much data as you can just, at some point you will meet a sentence where somebody says sheep are white, but still you will have this like distributional idea that the common sense information will be like the very rare pieces in the text. And the other idea is that you just leave the full text domain and you try to use something else. And you can use knowledge base. That's one option where you will connect sheep with color white. So you will build like your concept net or things like that. You can use multimodal learning where you have this image of a field where you see the animals and you see the color, they are white. Or you can have human in the loop, where you have like a human saying, oh, to the model, no, you're wrong. And all these are kind of starting to work, I think, better. Like human in the loop, we saw the first positive results, I think, this year. Well, like really interesting results, both in chatbots from the group of Fair New York and also from summarization from Cristiano. And also multimodal. Like very recently, there was the team of Moit Banzal, who show for the first time like multimodal model having improvements on text, pure text benchmarked by using images, which was very difficult actually to do up to now. And the idea, another idea, so there was this database. So I thought there's this option, and the database option, I think Yejing Choi has been maybe the one who kind of investigate this idea. So there was a lot of early trial, right, with this very large common sense database that we tried to build in the 70s and the 80s. And basically the idea of Yejing is that maybe it didn't work at that time, but maybe we can still do that today with the new tools we have, with like the crowdsourcing that we have, with this new approach that we have. And so she's been building a lot of interesting data set, I think. Maybe one of the more recent I can show you is Vino Grande. Is a successor to the, so we talk in the beginning of the talk, we talk about the Winograd schema challenge that was kind of solved. And so Vino Grande is the new way, is the new Winograd schema challenge. So she's been also building a lot of things, but I won't show you all the things, just show you a little bit about Vino Grande. So she's also been building this database of common sense, basically just asking crowdsourcer, well, what happened when, and just not physical common sense, but also like social common sense. What's happened when somebody hits someone that the other is pissed off, and then this one will have to like excuse herself. So you have a lot of things which are just, all the common sense, but just not like sheep are white, which is something like very practical and not social, but which is like a world fact. But also all these social kind of facts, which also are very important. And Vino Grande is maybe the new way to build this very large data set. And the idea here is that we use various ways to try to stimulate the crowdsourcer, and so that they don't incorporate too much in this data set the heuristics that we've been seeing in the NLI examples, for instance. So there are various ways you can give them anchor words, which are like words they have to use and kind of random. And so they have to create sentence with these words. So they are like it's like a little bit like constrained creativity. You have to use this, and so you find a new way to formulate something, and this will lead you to not use the very easy way to formulate example where you have all this bias, because we ask you to, for instance, give a contradiction, and so you will just use the word not, but then it will be very easy for the model to say, oh, there is not, so the label is pretty much always contradiction. But if you say, okay, now you have to formulate a contradiction, but you cannot use not, and you have to use palm tree, and so people have to like think a little bit more. They use also several levels of filtering with pre-trained models. So pre-trained models, we say they're very good at detecting these heuristics. And so here they say, okay, well, let's use them while we build the data set. And if they think that it's too easy to guess, then we take out these examples. And so the resulting thing is that they have like a new Winograd schema challenge, which is a lot more harder to solve. And the idea, there is still like a human level, which is about 94% accuracy. And you can still estimate that if the models are trained with infinite amount of data, they will reach human accuracy. but the amount of data required is really, really large. Here it's about, like you see, 1 million examples. So it's a lot larger than before. And if you just give like the number of examples that are given in WSC, in about 600, the models are very close to random. So this kind of work, this type of filtering here. Yeah, the more thing. And our last thing, so this is the last theme, which is also something I like a lot, is continual learning. And here the idea is, if we take the best paper of NeurIPS, if we take again GPT-3, right? It was very costly to train, so everybody can hear about that. And it was trained just before COVID. And so it's really bad because GPT-3 has no idea of what is COVID. Well, it's just a strong element of today's world. It defines pretty much everything we do in our life. And this model has just no way to have any idea about that. And it's almost impossible to just add, like, to model like GPT-3, just add a knowledge of COVID. We cannot just really fine tune a little bit by adding one Wikipedia paragraph about COVID, because we have what is called catastrophic forgetting, which is when you do this, usually the model kind of forgets entire part of its older memory, and you cannot really control what happens. You cannot control which part will be forgotten. So you can just do rehearsal and basically retrain fully the model, but then that costs another $10 million. So there should be another way, right? Humans, we managed to like get some new knowledge. We managed to learn about COVID without having to like see our whole life again, or without having to forget random part of our past. And so it's still pretty open. So I didn't have that, but we've been working just actually the two last months on this. There are some models now that they call non-parametric or like hybrid models, where you have a retrieval, like you try to separate the knowledge base. You try to separate the knowledge from the parametric part which process the knowledge. So usually these models, so it started with a model called Realm at Google. And there have been, well, it started a bit earlier, I think, but there have been also K and NLM. There have been a few models like that, where during the forward pass, the model will do like a retrieval step where it will query a database that was built by the model. That's the main difference with some previous trials. Like the model will also build itself the database, and we query it to retrieve some training. Basically you can see that as the model incorporating the training dataset. And it will query it and then use this as like additional input to do the prediction. And the nice thing here is that you can update this training set. Like this embedded training set is not exactly a training set. It's like vectors representing the training set, but you can update them. And so the model can learn new things using that. So a recent model that did that was a RAG model by Facebook, a retrieval augmented generation model. And so it's a question answering model where you can actually update the version of Wikipedia that it uses as a basic knowledge base. And so, for instance, if now there is a new president in the US, and so we can also update this information, take the current Wikipedia page, and the model will predict that the new president is the one it is. While BERT, for instance, will always predict that the president in the US is Donald Trump. So there are a very interesting way, I think, also here. Okay, and that basically, that's it for today. And that's all the kind of topic we're interested in at Huggingface and in our research team.
Thank you so much, Thomas, for the very interesting talk. It was really interesting and a very nice overview of what we probably should be thinking about right now when we deal with models. So we are slightly past 12, but I think we have time for one or two questions. So are there any questions from the audience? If not, I have a question. I particularly find the work on comparing Bert and Roberta in terms of efficiently learning from data samples, the discussion that you mentioned, that we can see that Roberta, while trained on more data, but when it also comes to fine tuning, it's the fact that it's, although it's the same architecture, but just with more amount of data during the pre-training, it's able to more efficiently learn from data samples. I found it interesting because part of my own research is focusing on low resource domain. And so I work with a lot of little amounts of data. And I wanted to hear your thoughts. So the way that we usually work, we try to come up with tricks to improve these neural models for low resource domain. And we see it, and lots of it involves transfer learning, and we see some improvement in the low resource domain. We are able to do better with low resource data. But that made me think that what other considerations should we take into account when working in low resource domain? Like if that trick really works for that like special language or that special setting, or for example, I focus on machine translation. For machine translation, how do you think we should also think in low resource domain in terms of, is it at the end of the day learning efficiently from this little amount of data? If like we know that with more data, it could learn it with more. In other words, if Roberta is able to learn more efficiently from data with more data, are these things that we do in low resource domain more generalizable?
Yeah, I think, yeah, I see what you mean. There's I think in low resource, there have been a couple of great papers also recently, but yeah, you probably have seen it's mostly out of FAIR, I think. And the XLM Roberta of Alexi was the Alexi Kono was the idea of extending this Roberta approach to like a lot of languages, and then just try to maximize the pre-training set, and then think that with a larger pre-training set, we can be also more data efficient and just get better performances in fine-tuning step. Yeah, I think that's pretty. I mean, on the one hand, I think it's a bit sad that we now have all like to start from these models because you would like to build everything from scratch ourselves. But I think if you want a good model, also a low resource settings, can be a low resource task or low resource language, you're very likely better off starting from an XLM Roberta model, or like models that was pre-trained on like a large amount of pre-trained data. In the end, I think the idea of all this comparison between Roberta and BERT is that as long as we are not like able to put the inductive bias ourselves, to design them in a way that are very efficient, then we're still better off like having them learn by the models of very large corpus. And that's, I think, the idea is that just Roberta is generalized better because using a larger pre-trained data, it's just learn more accurate inductive bias. That's kind of the idea, I think. Well, that's what I kind of take out of this. Yeah. But I still think, yeah, maybe there should be some way to kind of just not have to learn all this inductive bias from the data like we do here, but trying to like tailor them a little bit better. Yeah.
Yeah, I think it also like opens up a whole discussion also about unsupervised models. If you really have a model that with some trick you have trained it in an unsupervised manner, with, for example, MT, the absence of such inductive biases coming from a data source, what it means for the model.
Yeah.
Again, thank you so much for the talk.
Thanks.
I think there are no questions from the audience.
Actually, I have a question. Maybe it's a very quick question. Thanks, Thomas, for your very great talk. it was very informative. But I have a question related to inductive bias. So you talked about inductive bias problem, which is more in many kind of, we can say like classification problem or other kind of generation. But I was wondering if there are any kind of works that they kind of compare if we have any kind of inductive bias in the evaluation metric, like evaluation side of a generation model. Because it's a kind of very important problem when you kind of train your automatic evaluation metric on a specific domain. If your domain is kind of a little bit different from your training domain that you have trained your evaluation metric, then I think that again you will have that inductive bias. So I was wondering if you know, are there any kind of work for evaluating this kind of biasness in the evaluation metric on evaluation part?
Yeah, that's a good point. And so yeah, so that's the big debate I think right now in all this new evaluation metric when we can train a metric. It's a very big debate. I think they try to be careful. And the very first time people tried to do that, I think, was the Ryan Lowe paper, where there was actually they didn't get it published, but I think it was maybe not careful enough about this question of like basically your metric overfit, right, on your data set, and then you just don't evaluate anything when you use it. But now when you read like more recent thing like BERT score and blurred, they try to be more careful about that. Yeah, but yeah, I see what you mean. Yeah, definitely.
But I haven't seen that if they have kind of evaluate that bias problem. I mean, they're saying, okay, it's working well, but like it correlate well with human. But what if we kind of change like what if we have kind of completely new kind of data that we haven't seen during kind of training our evaluation metric? So then how could our evaluation metric do a good job there? Like this is a very like
Yeah,
open problem.
we need more evaluation for the evaluation matrix. I can I can agree. Yeah, no, that's yeah. I think it's still very open, right? And I don't think I'm very, to be honest, I don't think I'm very up to date on this. Like I don't know what was on the EMNLP like 2 weeks ago. I've seen a few papers that I haven't read yet on like related ID here, so I can send them to you. But yeah, but I don't know if people have found really solution. I think all this question of evaluation metrics in natural language generation is something that's evolving, but it's still very far from where we would like it to be, I think, unfortunately. Yeah.
Okay.
Yeah. No,
Thank
yeah, I don't have a very good pointer on this. Yeah.
Thank you.
Other than just the fact that basically in the end, human evaluation is still quite the gold standard when we want to do any kind of evaluation here, I think. Yeah.
Cool. Thanks.
So if there are no other questions, I think we can all thank Thomas for his great talk, really great overview of the topics.
Yeah, well, thanks for having me. And yeah, for those who have new riffs, have a nice conference. And for the other and everyone, just nice Christmas and everything. And see you around.
Thanks, everyone. Take care. Thank you, Thomas, again.
Thank you, Thomas.
Yeah. Have a good one.